What we know about Mars's interior structure and igneous activity. Before talking about igneous processes on a planet, we have to understand its interior. The fundamental driver of igneous activity is heat transfer from the inside to the outside of a planet. The planet's size, structure, and composition all influence the nature of this process. The InSight lander has given us a lot of details about the thickness, density, and composition of Mars's interior layers, because we now have direct measurements of seismic waves that have traveled through the planet. These give us much better constraints than orbiters and Martian meteorites that have made it to Earth. We can model Mars's interior using geophysical properties like its mass, moment of inertia, tidal response, and composition, which we know from orbiters and meteorites. But there are still many possibilities of how the planet could be structured. A planet's core is extremely important to its function because liquid core activity strongly affects mantle convection and plumes and can produce a magnetic field like the Earth's, which shields the planet from solar wind. We know from InSight data that Mars's outer core is liquid because S-waves don't travel through it, and that it is about 1,830 kilometers thick with an error bar of about 40 kilometers. This is larger than we expected, and its bulk density, the density of the inner and outer core combined, is relatively low for its size. This means that there must be lighter siderophile elements in metallic molecules that are dissolved throughout the iron and nickel alloy that makes up most of the core. This is probably mostly pyrite, FeS, because sulfur is the most abundant in Mars's mantle of these light elements, and is likely to bond with iron. Mars's core also makes up a larger portion of the planet than Earth's, which means that the mantle is relatively thin and doesn't reach the deepest phase transition that Earth's does. This highest pressure Bridgmanite phase in Earth's mantle is more insulatory than the lower pressure phase layers. The absence of this layer on Mars is very important because it allows heat from the core to dissipate outward faster than on Earth, which is a factor in how quickly Mars cooled after it formed. InSight data fit with models of a relatively cold modern mantle, which undergoes slower and possibly less homogeneous convection. Because Mars is about half the size of Earth, it cooled off much faster after its formation in the early solar system. The broad structural layers, the core, mantle, and early crust, formed by crystallization of the magma ocean that was present on early Mars as the planet cooled. There has probably been a lack of disturbance of this stratification because the mantle didn't retain enough energy to fuel as much mixing by convection as happens today on the Earth. The current seismic and heat flow data from InSight don't definitively show an average thickness of Mars's crust, but we know that the crust has about 13 to 21 times the amount of heat-producing elements, potassium, uranium, and thorium mostly, than the mantle. There are two models that fit with our data, a thin and a thick crust model. Based on the amount of heat-producing elements at the surface, the thin model has to have a higher concentration of them in the deep crust, meaning the deep crust would be more felsic than the surface. Either way, both of these models would call for an efficient process of magmatic differentiation to form a crust that has a higher concentration of these elements than the mantle below it. On Earth, this happens through the continuous volcanism that results from subduction of tectonic plates. But Mars doesn't have plate tectonics since its mantle is cold and slow, so something different must have happened. The cratering record shows that much of the crust formed early in Mars's history and was accompanied by substantial volcanism, so some differentiation happened during fractional crystallization of the magma ocean, which caused upward segregation of the heat-producing elements. And secondary differentiation also happened by more widespread igneous activity when Mars was still hot. Some places, like Gusev crater, have alkaline basalts, which must have formed by more prolonged evolution of a magma, in comparison to most of the crust we've studied, which is subalkaline basalt. The basalts analyzed in Gusev are about 3 to 4 billion years old and show that more evolved magmas were forming earlier in Mars's history. The mechanics of lavas and magmas should be much different on Mars than on Earth because of its lower gravity, which is about 0.375 times the Earth's gravity, and lower atmospheric pressure, which is about 0.06% of Earth's atmospheric pressure. Thermal evolution models of Mars suggest that volcanism should have ended more than 100 million years ago, but the ages of calderas on the main volcanoes in the Tharsis region, which is a vast volcanic province that covers about 25% of the planet, have been calculated with crater counting, and the calderas from the last episodes of volcanism on many of the volcanoes are only a few million years old, suggesting that they are still active or died out recently. Because of this, we can say that Mars has most likely had active, large-scale volcanism until at least 100 million years ago, probably more recently. Because of the ages of different types of volcanic deposits we've analyzed on Mars, there was also probably a broad transition from explosive to more effusive volcanism on Mars throughout time. This was probably related to Mars drying out and the near-surface water table descending as water left the planet. When explosive and pyroclastic eruption styles happen in silica-poor magmas on Earth, they generally occur when there is high water or other volatile content. So, as the amount of water on Mars decreased, the availability of volatiles in the subsurface may have decreased as well, leading to less explosive magma formation.